Welcome to our science series. Today we're diving into the fascinating world of physics to explore Archimedes' principle.
This principle tells us about buoyancy, while other objects sinks and why other objects floats. So, let's get started.
Here, we have a container filled with water and a few objects: a watch, a coin, and the cover of a pen.
Now, let's assume that the watch weighs 70 grams, the coin weighs 4 grams, and the cover of a pen weighs 2 grams.
Now let's see what happens when we submerge them in water.
As I place each object into the water, we can observe whether they float or sink. The watch sinks, the coin sinks, and the pen cover floats. But why is that?
According to Archimedes' principle, the buoyant force acting on an object submerged in fluid is equal to the weight of the fluid the object displaces. In simpler terms, if an object displaces more water than its own weight, it will float.
Let's measure how much water is displaced by each object. I'll start with the watch. The watch displaces 50 milliliters of water, which weighs 50 grams. Since the watch weighs 70 grams but only displaces 50 grams of water, it sinks.
The coin displaces 3 milliliters of water, or 3 grams. Since the coin weighs 4 grams, it also sinks. Now, let's try the pen cover. It displaces 3 milliliters of water, which weighs 3 grams. Since the pen cover weighs only 2 grams, it floats.
In summary, whether an object floats or sinks depends on the relationship between its weight and on the weight of the fluid it displaces. Archimedes' principle is not just theoretical. It has practical applications in shipbuilding, diving, and even in designing hot air balloons.
Thanks for joining me today to explore Archimedes' principle. Next time you see a boat or a balloon, remember the science behind why they float. Stay tuned for our next segment on Pascal's principle.
Bye-bye!
Welcome back. In this segment, we'll explore the Pascal's principle. This principle states that when pressure is applied to a confined fluid, that pressure is transmitted and diminished throughout the fluid. Let's see this in action.
To assemble the Pascal's experiment instrument, fill a smaller syringe completely with water and a larger syringe partially with water, ensuring both are free of air bubbles. Connect one end of a flexible airtight tube to the nozzle of a smaller syringe . And the other end to the larger syringe, ensuring tight, leak-free connections. Secure the setup by holding or fixing both syringes in a horizontal position.
Now that both syringes are filled, let's apply pressure to the smaller syringe.
As I push down on the smaller syringe, watch what happens to the larger syringe.
Wow!
You can see that the larger syringe moves up. This demonstrates Pascal's principle perfectly. The pressure I apply to the smaller syringe is transmitted through the fluid and causes movement in the larger syringe.
Woo!
Pascal's principle is fundamental in many hydraulic systems. For example, hydraulic brakes in cars, and hydraulic lifts use this principle to amplify force. Take hydraulic brakes. When you press the brake pedal, it applies pressure to brake fluid in the system. This pressure is transmitted through the fluid, activating the brake pad on a wheel seamlessly. This allows for effective stopping power.
So remember, Pascal's principle shows us how pressure works in fluids and has numerous applications in our daily lives, from cars to construction equipment.
Thanks for watching. Now that you know about Pascal's principle, stay tuned to our final segment on Bernoulli's principle.
Welcome back. In our final segment today, we will be exploring Bernoulli's principle. This principle states that an increase in the speed of a fluid occurs simultaneously with an increase in pressure or potential energy of that fluid. I have a simple demonstration using this piece of paper and my brand. Watch closely as I blow across the top of this paper. You can see that as I blow air over the top of the paper, it lifts up. This is because when air moves faster over the top surface, it creates lower pressure above the paper compared to the higher pressure below it. Let's try another experiment with this lightweight ball. Watch what happens when I blow air. The ball rises into airflow. Wow! The ball rises to the airflow. Again, this occurs due to the differences in pressure created by the fast-moving air unit. Bernoulli's principle has many applications in real life. For example, airplane wings are designed with a special shape that allows air to travel faster over the top surface than underneath. This difference in speed creates lift, allowing planes to fly. Similarly, Bernoulli's principle explains how atomizers work, like those used in perfumes, where fast-moving air creates low pressure that draws liquid up into a fine mist. In conclusion, Bernoulli's principle helps us understand fluid dynamics and has significant implications in aviation, engineering, and even everyday products. Thank you for joining me today on this scientific journey through Archimedes, Pascal's, and Bernoulli's principles. Keep exploring and stay curious about the world around you. Welcome back in this segment of
Welcome to our science series. Today we're... Here we have a container filled with water and a few objects. Number 6 depends on our relationship with its weight and the weight of the fluid. Weight of the fluid. Why they float.